Why does L2 regularization matter in the world of machine learning? This might be a question that resonates with many, especially those who delve into the intricate art of creating predictive models. So, without further ado, let's unravel the mysteries of L2 regularization. Imagine a scenario where a machine learning model is trained on a dataset. The model learns from the data, but sometimes it learns a little too well. It starts to pick up on the noise, the random fluctuations in the data that don't represent the true underlying patterns. This is what we call overfitting. It's like studying for an exam by memorizing the textbook word for word, rather than understanding the concepts. Sure, it might work for that particular textbook, but what about when you're faced with a different book, or real-world situations that weren't covered in the book? You're likely to fail. Similarly, an overfitted model might perform well on the training data, but it will struggle to generalize to new, unseen data. This is where L2 regularization comes in. It's a technique used to prevent overfitting, to help the model generalize better. It does this by adding a penalty to the loss function, the measure of how well the model is doing. This penalty is proportional to the square of the magnitude of the coefficients. In other words, L2. Regularization discourages the model from relying too heavily on any one feature, thereby promoting a more balanced, generalized model. Think of it as a teacher who encourages her students to understand the concepts, not just memorize the textbook. The students might not do as well on the textbook-specific questions, but they'll be much better prepared for real-world situations, for questions that weren't in the book. In the context of linear regression, L2 regularization is also known as ridge regression. Here, the penalty term is the sum of the square of the coefficients, hence the alternative name, squared L2 norm. The effect of this is to shrink the coefficients towards zero, but not all the way to zero. This is a key difference between L2 regularization and its L1 counterpart, lasso regression, which can shrink some coefficients all the way to zero, effectively excluding them from the model. So, to summarize, L2 regularization is a powerful tool in the machine learning toolbox, used to prevent overfitting and promote model generalization. It does this by adding a penalty term to the loss function, proportional to the square of the magnitude of the coefficients. This encourages the model to spread its reliance across all features, rather than leaning too heavily on any one feature. In linear regression, L2 regularization is known as ridge regression, and it shrinks the coefficients towards zero, but not all the way to zero. This is a subtle but important difference from L1 regularization, which can exclude features from the model entirely. Remember, understanding the concepts is always better than memorizing the textbook, and L2 regularization can help your machine learning models do just that.